Hello and welcome to the 13th lecture of the machining science course. So, in our previous session we were discussing the principles of measuring cutting forces. Now, we have seen that for different processes like turning, milling, drilling or grinding, the forces are different and therefore, the measuring principle is also different. We have discussed the most basic element like axially loaded member, then we discussed the cantilever beam, then we discussed the ring type structure, and we have seen that in the ring type structure there are certain disadvantage, that it is not very stable in the horizontal position, in the sense that it can actually roll under the action of the axial force. So, therefore, the ring type structures are modified in terms of the octagon. As you can see from the slide, this is an octagon and this has the principle of the ring type dynamometer, but it is more rigid. And here this is the another view of the ring type dynamometer from the side. So, the photoelastic examination of such rings reveal that the strain nodes now occur at 50 and 90. So, if you remember, in the ring type structure it was 39.6 degree, all right. So, these nodes are found out, I once again repeat, from the photoelastic examination, and the photoelastic examination of such octagon structures revealed that the nodes are at 50 degree and at 90 degree. So, at 90 degree the sensors or the strain gauges, as we are telling, this will be, these sensors will sense the thrust force like Fq as shown here, and the axial force, this is the Fp or the tangential force Fp, this will be sensed by the sensors when they are placed at 50 degree with respect to the vertical axis. So, this will be 1, 2, 3 and 4. So, 1 prime, 2 prime, 3 prime and 4 prime, and these are 1, 2, 3, 4. 1, 2, 3, 4 once again will sense the Fq, and 1 prime, 2 prime, 3 prime and 4 prime will sense the tangential force Fp. Now, at 90 degree the magnitude of the magnitude of the strain, it will be plus minus 1.09 Fqr divided by EBT square. So, this remains the same as in case of the ring type dynamometer or ring type structures, whereas in case of 50 degree, at 50 degree angle from the vertical axis, at these nodes the strain will be plus minus 1.4 Fpr divided by EBT square. Now, Fp, because these are the sensors which will sense the force Fp. Now, once again, when the strain at 90 degree is measured, on these sensors 1, 2, 3, 4, there is no effect of the Fp, that is one thing that we have to maintain, and vice versa, that is on the 1 prime, 2 prime, 3 prime and 4 prime, there is no effect of the Fq, they will only measure the force Fp. Well, now, let us see the based on these principles like cantilever beam or ring type structure or octagon, what are the dynamometers that are designed and made to measure the cutting forces. So, the dynamometer requirements are, these are the 5 requirements. One is the sensitivity, the dynamometer has to be very sensitive, meaning that even a small force should be sensed by the sensors which are there in the dynamometer. Second is the rigidity, should be sufficiently rigid relative to the rest of the machine tool, so that it does not affect the cutting condition by causing excessive vibration and chatter. So, chatter is the self excited vibration. In order that the interference with cutting condition is small, the natural frequency of the dynamometer should be several times the cutting frequency. Otherwise, what will happen, that it will match the natural frequency of the dynamometer and it will be in the resonance mode. So, the vibration will be too high. Third requirement is the linearity, the relationship between the magnitude of the cutting forces and the deflection, which is called the linearity, should be perfectly linear without any hysteresis effect. This you understand that as it goes up, it will come back along the same line. So, there is no hysteresis there. So, this is the relationship between the magnitude of cutting forces and the deflection. So, as the cutting forces are increasing, the deflection should increase, and then when the cutting forces are taken out, so the deflection should come back to the initial position along the same line. So, without any hysteresis. Now, fourth one is the interaction. There should be negligible cross sensitivity. By cross sensitivity, we mean that one set of sensor should not sense the force of other force, okay, which it is they are not supposed to sense. Meaning, I told you earlier that 1, 2, 3, 4 will sense only the FQ, and the effect of FP on the 1, 2, 3, 4 will be minimum or no, negligible. So, therefore, we say that interaction, there should be negligible cross sensitivity. This is called the cross sensitivity. And of course, the stability, the dynamometer has to be stable enough, so that the whole system is not affected by the stability of the dynamometer itself. Now, let us take some examples of machine tool dynamometers, the principle, that is the design, how they are actually made. Look at this design. This is the same as based on the principle of the cantilever beam, and here is the structure, okay, and 1, 2, 3, 4, these are the 4 sensors at this surface and at the surface opposite to this. On this surface, there are 1 prime, 2 prime, 3 prime and 4 prime. Okay. This is the one, this is the surface which is 90 degree from this. So, there are 8 strain gauges 1, 2, 3, 4 and 1 prime, 2 prime, 3 prime, 4 prime. So, 1, 2, 3, 4 as you understand, like we have discussed in the case of the cantilever beam, it will sense the force which is acting like this. So, this is the FQ, okay, which can be considered to be a thrust force. Perpendicular to that, which is the FP, which is cutting force, it will be sensed by these 1 prime, 2 prime, 3 prime and 4 prime sensors, and the effect of FQ will not be there on the 1 prime, 2 prime, 3 prime and 4 prime, and vice versa, that is the effect of FP will not be on the 1, 2, 3, 4 sensors. Okay. So, this is an example of the machine tool dynamometer which is used for the turning. So, this is the turning dynamometer. So, as you can see that this is a cantilever beam, this is the tool post, you can consider this to be a tool post, and the tool is protruding out, which will give you the moment, and we know the distance between the force, this point of action of the force and where the sensors are located. So, this force into the length will be the moment, and I have shown it to you earlier while discussing the cantilever beam, that how from the moment we can find out the force. Okay. So, basically we will be measuring the strain, from the strain we can find out the moment, and if we know the distance, then from that we can find out the force, because the force into distance is the moment. Okay. This is another dynamometer, which is principle of the dynamometer, which is the drilling dynamometer. Now, here the drilling forces can be measured, that is drilling forces, I will once again remind you that this is the thrust and the torque. So, here as you can see that this is on the principle of the ring type dynamometer. Here we have the arms or spokes, all right, and on this we have 1, 2, 3, 4, 5, 6, 7, 8, and then we have the 9, and on that other side it is 10. Then we have the 11, 12, 13, 14 and 15, 16. So, there are altogether 16 elements or 16 strain gauges or 16 sensors, because as I said in the beginning that these can be either strain gauges or piezoelectric elements which will sense the force. Okay. So, 1, 2, 3, 4, 5, 6, 7, 8, these sensors will measure the torque, because as you can see that if torque is provided, so these arms will be deformed, and along with the arms these sensors will be deformed and they will send the signal which will be equivalent to the force or the torque which is being applied. Whereas, that thrust, if you look at the other view, the thrust will be sensed by 9, 10, 11, 12, 13, 14, 15, 16. Okay. Because as the thrust is applied, so then this element will be deformed in the vertical plane, okay, and then the 9, 10, 11, 12, 13, 14, 15, 16 will be affected and they will sense this. So, if you see, for example, in this section, if you take a section here, so here you will see the 9, 10 and here you will see the 13 and 14. So, if you apply the torque, these 9, 10, 13, 14 and all others up to 16, from 9 to 16 they will be affected and the torque can be measured equivalent to the deformation of those strain gauges in these cases. Okay. Now, next is the extended octagonal ring dynamometer as it is shown here, because the octagonal structure that I have shown as an improvement of the ring type structure, this is still not enough to withstand the rigidity that is required for milling or grinding, for example. So, these are the dynamometers which are used for grinding or milling. By the way, I will like to clarify one thing, that here probably you understood that when this kind of dynamometers, they are used, let us say this is the dynamometer, okay, which is used on the top of the workpiece, which is to be on the this is the, let us say this is the dynamometer. This dynamometer is placed below the workpiece and this is the workpiece, all right, workpiece. This is the dynamometer, and when the drill will be, a hole will be drilled here. So, there will be a thrust and there will be a torque imparted by the drill, and this dynamometer with the principle here as it is shown here, the torque will be sensed by 1 to 8 and the thrust will be sensed by 9 to 16. So, this is just to clarify that how it works. So, the dynamometer is placed below the workpiece, so that the dynamometer senses the torque and the thrust being imparted on the workpiece by the drill. Similarly, here also the workpiece is placed on top of this, okay. This is the workpiece, and let us say it will be milled or it will be ground. Okay. So, during the milling and the grinding, the forces that will be imparted on the workpiece, that will be sensed by the dynamometer. That is, either it is a thrust or it is a moment or it is an tangential force. Okay. So, here the design is the same as in case of the octagon, like at 90 degree and at 50 degree with respect to the vertical axis. We have the 1, 2, 3, 4. These are the sensors which will sense the thrust force Fq, here it is Fp, and 1 prime, 2 prime, 3 prime and 4 prime, these sensors will sense the tangential force, let us say Fq here. Okay. So, this is the dynamometer which is once again extended octagonal ring, because the rigidity is extended, rigidity is increased by that. So, circular or octagonal rings are not useful for it by itself, but can be made sufficiently stable by extending it. So, here the rigidity and the stability has been increased by extending the octagonal structure. This is suitable for horizontal milling, as I said, horizontal surface grinding, etc. So, for example, here you can assume that the milling cutter or the grinding wheel, it is working, okay, and the feed is given. So, therefore, the torque and the thrust will be sensed by these dynamometers 1, 2, 3, 4 and 1 prime, 2 prime, 3 prime and 4 prime. Okay. So, next to this our topic will be tool wear and tool life. So, let me give you a preamble that this is a very important topic, because the tool is a very expensive material. The tool material is very expensive, because the tool material is harder than the workpiece material, that is one thing. Tool material should have less wear than the workpiece. So, therefore, all these properties will make the tool material very expensive, and therefore, we cannot afford to have the tool wear very fast. So, if tool wears out very fast, in that case we are incurring a lot of cost on the machining, and the end product that we will be producing, that will be very costly, because the tool wears out and we are making expenditure on the tool. So, modes of tool failure, if you see, so these modes are several. For example, it can be fracture failure, tool can be failed by fracture, it can simply break, cutting force becomes excessive and or dynamic, leading to brittle fracture. So, brittle fracture is simply it breaks, all right. Now, the second factor could be the temperature failure, that is the thermal failure. Cutting temperature is too high for the tool material. So, it will be thermally deformed and it will be failed. So, the tool failure, one of the reasons is the thermal failure therefore. Third is the gradual wear. During the machining it is in constant touch with the or constant contact with the workpiece. On the rake face the chip is moving continuously, there is a friction. At the flank face it is rubbing with the already machined surface and the workpiece. So, therefore, these surfaces are in constant contact with the workpiece at a high speed or medium speed or at certain speed, and therefore, there is a gradual wearing of the cutting tool. Now, the mechanism of tool wear can be either abrasion or adhesion or diffusion. So, it can be either one of them or a couple of them together, in the sense by mechanism we mean to say the factors which are responsible for the tool wear. So, what is abrasion is if one of the surface contains very hard particles, then these during the process of sliding may dislodge material from other surfaces by ploughing action. So, if you put a chalk, if you write something by chalk on the blackboard, you will see the chalk is wearing out, because the blackboard has harder particles and it will abrade the chalk material. So, that is why it is called the abrasion. Second mechanism could be adhesion. This is when the bodies of similar nature are in contact, the asperities tend to get welded. Sliding causes fracture of these welded junctions and material is lost from both the surfaces. This we have discussed while discussing the sliding friction, for example, that basically the two surfaces are meeting on the asperities, and when the normal force is becoming higher, then those asperities will be welded, and during the sliding these asperities or welded asperities will be sheared off. Because of that shearing of the welded asperities, there will be small particles which will be broken from there and it will start abrading. So, this is called the adhesion mechanism, and this is one of the factors which is responsible for the tool wear, and that is why we call it as a mechanism of tool wear. Third mechanism is diffusion. Atoms in a metallic crystal lattice always move from higher concentration to that of low concentration. The process is known as the diffusion. Therefore, we can explain that why tools wear out, because tool is harder material and it has the more atomic density. So, therefore, during the cutting process, when it is interacting with the workpiece, the atoms from the tool which is at the higher density will move from the lower density of atomic structure, which is the material, workpiece material, and therefore, the tool wears out. So, that is called the diffusion, and this is one of the factors which is called the mechanism of tool wear, which is one of the mechanisms of tool wear. Now, how the tool wears out? As I said that chips are moving continuously over the rake face of the tool. So, there is a wear at the rake face, and the flank face is in continuous touch with the already machined surface. So, there is a wear. The progressive wear of a cutting tool first occurs in the flank face, okay, which is in contact with the flanks with the workpiece surface, in the form of a wear land due to rubbing against the newly machined surface. So, this wear is known as the flank wear. So, this is shown as the flank wear. Okay. Now, as a result of chip flowing over the rake surface, rake face, wear also takes place on the rake surface in the form of a crater, which is known as a crater wear. Now, flank wear can be measured by means of a measuring microscope. So, that is, you must be familiar with the tool microscopes, for example, where you measure the tool angles and so. So, under the tool microscope you can find out the flank wear or the length or width of the flank wear. Crater wear can be evaluated by means of a surface analyzer, because crater wear is something which is a dip on the rake face of the tool. So, therefore, if you have a surface analyzer, the surface analyzer can measure what is the depth of the crater. Crater wear is formed at higher speeds when diffusion has been considered to play a major role. So, normally as we said that as the machining starts, we have the flank wear, and at higher and higher speed, when the chip is flowing at a higher velocity, higher speed over the rake face of the tool, the crater wear takes place. So, therefore, crater wear, for crater wear the responsible mechanism is the diffusion, because it is at the higher speed, and for diffusion what we need is the higher temperature, okay, and at higher speed the temperature becomes high. So, it actually facilitates the diffusion process. So, therefore, at higher speed the crater occurs, and at lower to medium speed the flank wear occurs. Now, let us see the flank wear, how the flank wear progresses with the time of cutting. So, the curve goes like this, this is a popular curve, and this curve is explained in the following way, that initially the tool is sharp, there is a lot of stress concentration around the sharp tool. So, therefore, initially as it comes in contact with the workpiece, there is an initial break in. Okay. So, this is called the break in period. After that, there is a steady wear because of the rubbing of the flank face with the already machined surface and the sliding of the chips over the rake face of the tool. So, this is the steady state wear region, and the wear rate will be uniform here, whereas in the first stage the rapid initial wear will be there. Then after some time the flat will be so high, that is the flank wear flat, that it will actually can fail any time after this point. So, this is called the failure region, or sometimes it is also called the catastrophic failure. Okay. So, this is the accelerating wear rate. Wear rate will be very steeply accelerated because the wear flat has gone up. So, the temperature becomes more, forces become more because of the flat which is being created on the flank face of the tool, and the more crater on the rake face of the tool. A tool that no longer performs the desired function, but not that it is unable to cut at all. It is said to be reached the end of its usual life and failed. At this point the tool is resharpened and used again. So, when we say the tool life, definition of tool life is very difficult, in the sense that when you will say that the tool life is over. So, overall we say that tool which is not performing as per our criteria, then we say the tool life is over, and then we resharpen the tool, so that the previously made geometry of the tool is again settled or again given to the tool. So, for example, here it is shown the time of cutting and the tool flank wear. Okay. Now, for different cutting speeds, the curves will be like this. So, usually at higher cutting speed, the flank wear will be more. So, this is the lower than this, and this is even lower than that. So, as you can see that at lower speed the flank wear is less, or the less steep curve, but at a higher speed the flank wear is more. This is very obvious. Okay. Now, if we draw these curves for different velocities, and then we draw a line which we say that we should not allow the flank wear to grow beyond that. Okay. So, in practice it is used as 0.3 millimeter and up to 0.5 millimeter. 0.5 millimeter is normally not allowed, it is actually 0.3 millimeter. So, within that 0.3 millimeter, if the line is drawn, in that case we will be knowing that what is the life for each of these velocities, because then the time of cutting can be assumed to be the tool life. Okay. So, at this, for example, since it has reached this criteria of the flank wear and we do not want the flank wear to grow beyond this point. So, the tool life will be this. For this speed of 130 meter per minute, for example, then here the tool life will be this, and at this point the tool life will be this. Okay. So, the Taylor's tool life equation describes that how the cutting velocity affects the tool life, particularly this in this formula it is shown here, that V t to the power n is equal to constant, and this is popularly known as the Taylor's tool life equation, which actually relates the tool life, this is equal to C by 1 by C by V to the power 1 by n. Okay. So, it is showing that how the cutting velocity affects the tool life. So, this is the tool life, okay, T, and the tool life, as we said, that we will actually define that it should not go, let us say flank wear should not go 0.3 millimeter. So, at 0.3 millimeter we are drawing the line, and that line wherever it is intersecting, that is the point which we can take as a tool life. Okay. So, therefore, if you draw this tool life and the tool life versus the speed, so it will actually be like this, that this is, let us say t, let us say it is a log curve t and it is a log of v, okay. Or we can say that this is, let us say this is t and this is log v. So, this line will be like this, which is actually given as equation is V t to the power n is equal to c. Okay. So, this curve is taken from these experiments. That means, these tool life values are placed here against the cutting speed which are here. Okay. So, as I said that for 100, for example, it is this, for 130 it is this value and so on. So, these values are put in the log scale and then we are getting this. So, as you understand that if you are extending this curve and wherever it is intersecting, so this will give you the value of c, because here the t is equal to 1. Okay. So, this value here will be given as c, all right. And of course, the t, as you understand that if you give an unit value, so this is n, this is the n here. So, n and c, these are constants, n c these are constants, and v is the cutting velocity, t is the tool life, this is n constant, this is c constant. Now, c and n, these constants, they will actually depend on the, it is a function of the combination of the materials, okay, materials of tool and the workpiece, tool and the workpiece. Depending on the tool and the workpiece material combination, you can find out the values of the n and c, and which are normally given in the material handbook. Okay. Now, n is the slope of the plot, as I am showing that, this is the slope, and c is the intercept on the speed axis. Okay. So, on this here, since the t is equal to 1 here, so for t is equal to 1, this will be the c, right. So, therefore, this intersection will have the value of the c. Okay. Now, the variables, so as I said that t is equal to c by v to the power 1 by n. Now, the t can also be expressed as dependent on the cutting velocity, not only cutting velocity, but the feed and the depth of cut as well. Okay. Here what we are showing, or what F. W. Taylor has shown, that the t is dependent on the cutting velocity. But apart from the cutting velocity, the tool life also depends on the feed and the depth of cut in the following way as it is shown here. This also, as you understand, that it can be experimentally found out, and after Taylor's tool life equation was invented, the further research with the help of taking the feed and the depth of cut as the parameters, variable parameters, the experiments were made, and this is the result which have been found out. So, here it has been seen that 1 by n is more than the power of f, and which is more than 1 by n 2. This actually shows that the effect of velocity, which is power of which is 1 by n, which is more than the power of f, it has the more effect than feed than the depth of cut. So, indicates that the cutting speed has greatest effect on the tool life, followed by feed and then depth of cut. Okay. So, this is an important formula therefore, because it actually shows, this is also sometimes called the extended Taylor's tool life equation, where it relates, the tool life is related to cutting velocity, feed and the depth of cut, whereas the Taylor's tool life equation relates the tool life with the cutting velocity only, alright, because Taylor's have done that long time ago, where he did not have the computer facilities and the proper experimental facilities that we are having right now. So, afterwards the extended Taylor's tool life equation have related the tool life with the cutting velocity, feed and the depth of cut. The rest of it we will discuss in our next lecture. Thank you for your attention.